Okay, welcome to Cirencester College video about chapter 24, the last chapter that we've got to do before Easter, and then we will have revision time after Easter, which is brilliant. Okay, somebody asked me to see me wearing my hat, so I'm going to wear my hat. Okay, let's get cracking on with it then. So let's share my screen. Okay, so we are on to the D block elements. Last section we were looking at the half equations for these. Okay, I will show the half, we've got the half equations for those. Let's just put those back. Let's go back a step. Yeah, okay, so we did these half equations, okay, from the redox, and if we balance this one out, we get that, okay. The way we do it, we can do it via oxidation numbers. First, we need to check which element is going to be the one changeable. In this case, it's going to be the manganese, or which happens to be a D block element. We'll come back to that in a bit. So +7 here, because the overall ion is -1, oxygen's -2, so that's -8 overall. That must be +7. This is +2 or +2 oxidation number. So we've gone from +7 down to +2, so we need to add 5 electrons to do that. So plug those 5 electrons in. Then we need to balance up the oxygens. Well, we've got 4 of them, so therefore we need 4 waters on the other side to balance up these 4 oxygens. That leaves us with a problem because we've now got 8 hydrogens. Well, we can sort that out by doing HH+. Then let's just check that we've got all our charges balanced. This side is 2+ on this side. Well, this side is 5-, 6- +8+, so -6 + 8 is +2, so both sides +2. We can do a similar sort of operation on the dichromate, we get that. Okay, so if you want to, you can stop and check, stop and work it through in your head. And also we have this one here, which is useful because it's related to what we did in the 23.3, which is iodometry. Okay, so please keep up the exam papers. Yeah, we tell you what is the best stuff that helps you to do well. So do lots of exam papers, marking yourself and checking it. And you should have a spreadsheet version of the checklist, which you can do R, G, and A. So R is red, G is green, A is for amber. And then that last column on that spreadsheet that we've set up for you, you can then put in those letters, and it will automatically, rag rate it for you. Yeah, red, amber, green. And do not revise the stuff that is in green, or at least look at the stuff in red and amber and spend more time in your revision schedule for that. Okay, so getting that booklet done as well, chapter 23, 24. So in the diagram here, we have got where the transition metals are. Okay, so this is the D block. So all these elements in this sort of palish pinky color or peachy color are the D block. Okay, however, they are not all transition metals. We'll come on to that. So this is our last topic. Okay, we'll be looking at the physical chemistry and looking at transition elements. So we need to describe elements titanium to copper as transition metals. What about scandium and zinc? They're not. Okay, they're not transition metals. They are D block, but they're not transition, and we'll see why in a minute. You need to be able to do the electron configurations of those and think about the ions. And also understand that transition metals have more than one oxidation state. Okay, and that's a key definition. They have more than one oxidation state, which scandium and zinc do not. Okay, apart from 0 and their common ions. And they get the transition metals, not scandium, not zinc, will form coloured metal ions. Okay, and they are also good as catalysts. Okay. And finally, we can, obviously we're going to identify that scandium and zinc, here we go again, are not actually transition metals, but they are D block. Okay, and we also have some issues with the C metals in that first period of transition metals, the C ones, which is chromium and copper. They don't follow the normal pattern. So the key words we've got are, well, subshell you should know, oxidation state we should know, coloured metal ion, fairly obvious. Okay, and transition element is an element of the D block element that forms an ion with an incomplete D subshell. Okay, so we'll look at that because that will mean that scandium and zinc are not transition metals because they do not form ions with incomplete D orbitals. So, okay, first row runs from scandium and zinc. Scandium and zinc hammering that, are not D element, are D block, but they're not transition elements. Okay, scandium forms Sc3+, and therefore all its d orbitals are empty. And zinc forms Zn2+. Okay, the d orbitals are full, but the 4s2 have gone. So that's where it loses electrons from, and it doesn't lose them from the d orbital. So, it has a complete d orbital, whereas scandium has a completely empty d orbital. Okay, so the properties of transition metals, the fact they are colored, they can be catalysts, they can form strange polyatomic ions with oxygen, is because they have an incomplete d subshell. So first row D block, we could use AR, okay, and then you should go through question 1 and 2 in the booklet just to make sure you're okay with that. Do check it, and once you have finished and you checked, you think you're okay with it, then we carry on. Okay, so here are what you should have written down, and you can see that chromium and copper have been highlighted. Okay, they do not fit the pattern. Okay, but if you think carefully about what's happening, they do make a lot of sense. Okay, so if we come down to chromium, okay, its electronic structure is not 4s2 3d4, okay, it's 4s1 3d5. And what has happened is, because the 4s and the 3d orbitals are very close together in energy, one of the s electrons has been pushed up into the d orbital to mean that the d orbital, which has got d subshell, which has got 5 separate orbitals, 5d sub orbitals, have got 1 electron in each. 1, 2, 3, 4, 5. Okay, rather than having 4 and 2. Okay, so what happens? We get that. Okay, 1 and 5, and that means you've now got 2 half-full shells, as opposed to 1 full shell that's quite, very close in energy to those, and 1 not full. Not full is really bad. Okay, not full is really bad. Half full is not so bad. Okay, full is good. Okay, or empty. Full, empty, and half full are pretty good, but not full is very bad. Okay, so then we go down to manganese. Okay, so 4s2 3d5, and keep going. Eventually we get down to copper. That ought to be 4s2 3d9, but wouldn't it be a bonus if we managed to have a completely full D shell? Well, yes, we have. Okay, so we push 1 of the electrons up from here, the 4s. Remember 4s, so 4s is down here-ish, 3d is here, they're very close together. The 4s is slightly closer to the nucleus, slightly lower energy, but therefore the electron can jump up to here and then spread out to make sure that we've got 3d10 full. That's our structure, or that's our electronic structure with those two problems. Okay, so can we do manganese? Yep. Okay, can we do cobalt? Yep. Okay, what about V3+? Right, so what has happened here? Let's go back. Let's look at vanadium's electronic structure. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Okay, how does it form a +3 ion? Okay, well, what it's done is it's lost its 4s2, because if I lose those 2, I can lose those 2 pretty easily, because then I've got an empty shell, which is cool, okay, or good, a more energetically stable position, and then I will lose 1 more electron from 3d, and now that d orbital is still incomplete, and we have an ion. Okay, copper 2+. Okay, so what has happened here? Well, we've lost 1 from, well, the one that's 4s. Well, what's happened is basically the one that jumped up to become 3d10 has jumped back down to make it 4s2, and then we can lose those 2. Okay, and so we've lost them from the 4s. Okay, chromium, similar thing. Okay, we've got it would have been 4s1 3d5. Okay, so what's happened is 1 has dropped back down to the 4s, lose those 2, 4s gone, and then we lose 1 more. Okay, and we then have an incomplete shell. So we can have those incomplete shells. Similar position, nickel would be 4s2 3d8. It just loses those 4s2s. Okay, so obviously there's some answers to those transition elements. Okay, so this is it filling, and I can just go through this. You can probably read it. Okay, so this is going through for chromium, and it's showing that it jumps up. Okay, Right, manganese, we're back to the normal pattern. Okay, iron fills the next one, cobalt, nickel, etc. And the copper, again, we've got this idea of this one electron that was here being pushed up into here to make this completely full, and this is half full. Okay, and then zinc, okay, is across the top. So ions, when electrons are removed, they come from the 4s orbitals first. So if you've got copper, it's going to one of the electrons is going to drop back down and then be removed. So for copper, here's how its structure is. So it's 3d10 4s1 or 4s1 3d10. You could write those either way around. So the titanium is 3d2 4s2. We cannot lose stuff from the 3p6 because it's much lower or closer to the nucleus. So it's being held quite tightly. But the 4s and the 3d are quite close and can overlap. So here are some ions. Now the ones in red are the more common ions, yeah? So that makes a lot of sense. Copper plus, yeah, lose one of the 4s1, that's cool. Or once I've lost that, I can then make copper 2 plus because when the 3d10, the 10th electron has jumped back down to the 4s, and then we can lose that. So we've lost those 2 electrons. Okay, and then the titanium, we've got at least, well, we've got 3 ions there. We've got titanium 2 plus, 3 plus, and 4 plus. And hopefully you can see where those have come from. So titanium is 4s2, 3d2. Okay, so to make titanium 2 plus, we've lost the 4s, the 2 4s electrons. Titanium 3, we've lost the 2 4s electrons, plus we've lost another d1. Okay, and finally titanium 4 plus, we've lost all the d's and all the s's. So loads of good uses for them, for the transition metals, a nice iron post box, because you all write letters all the time, don't you? Then we've got chromium. Yeah, chromium can be used for chromium plating to make steel last longer. Got nickel copper alloy in coins, so got a range of American, well, actually just American coins there. But also, interestingly, the amount of copper that was in I think it's 1994, you could check it out. But pre-1994 coins, the copper was much higher in content in our British coins. So they had to change the composition of the alloy because the coin, even though it said the coin was worth 2p, it was actually worth more than that in terms of the amount of copper in it. So titanium, excellent for hip replacements, very strong metal, quite light, and very unreactive. And stainless steel, obviously, if you make your cutlery out of that, it's going to last a lot longer. Iron, carbon, and 11% chromium. Stainless. So melting and boiling points, what's going to happen into these metals? So the type of structure, well, they're all going to be giant metallic lattices. And what will be the trend across a period? Well, let's think about that. Are we getting bigger atoms, or no, we're not. We haven't got another shell. So the atoms aren't necessarily getting much bigger, but what we have got as we go across the period is more protons in the nucleus. So they're going to pull in the electrons tighter. So what we should see is that as we go across the period, it goes up, it does, but then it sort of comes back down again, okay? So but basically they have got higher melting points and boiling points in group 1 and 2, much higher. Strong metallic bonds because we've got small ions, okay, and close packing and large charge densities. Okay, and you can see the densities there as they go across, and they actually densities do just get bigger and bigger. So why would these transition metals have smaller ions as you go across the period? Because they've got more protons and sometimes higher charges. So for instance, I could have vanadium 3 plus it's already got protons in there pulling electrons in. So that could be quite a small ion. Okay, so we're going to go on to this next slide where we look at what the possible oxidation numbers of these metals are. Okay, you may need to look up the colors to work out what color each metal compound is in that color. This is in textbook page 138. So when I move on, okay, here is this table. Now you might have to have an extra row at the bottom to fit the +1 in for copper. But everything in red is the common ion. So manganese could be +7, or sorry, common oxidation states. So manganese could be +7, +4, +2. Okay, you can, in fact, there's an experiment we can do with chromium where we could stabilize the +4 version of chromium. It's not particularly stable and would convert to +3 relatively quickly. So why have they got these variable transition states? because it's similar in energy to remove 4s and 3d. And notice they go up towards the middle, towards manganese, and then they start to come back down again. So yeah, so they're going up in the middle and come back down again. Okay, okay, let's get recap. What is manganese? Is electronic structure. So let's flip back to that. Manganese electronic structure. There we go. Okay, so 4s2 3d5. Let's go back and let's see what its maximum oxidation number is. Okay, so its maximum oxidation number is +7. 4s2 3d5. Ah, okay, that's it. Yeah, so that's what its maximum oxidation number is going to be +7, because it could lose all its Ds and all its S electrons. So why have they got variable oxidation states, similar energies? Okay, what trends are? Why does it stop after manganese? Well, yeah, I'm actually ripping off. By the time I got to manganese +7, I could have to rip off 7 electrons, and then get more than that. It's just the ionization energy is too high. And as the third ionization increases, so that's the ionization energy required to rip off a third electron from a substance, the stability of the +2 is going to increase. Okay, so why is it useful? They can be used as oxidizing, reducing agents and catalysts. The ones in red from that table are the most common ones. You should have this in your booklet. Okay, write it down. So catalysts, what do we need to remember? We need to remember they provide alternative pathway, okay, like the diagram shows. Okay, obviously we end up with more successful collision per second. The catalyst should remain chemically unchanged at the end. Catalysts are used to speed reactions up or make them work at lower temperatures and pressures. Also, we could promote a specific reaction route which gives us better atom economy. Okay, they can save energy, therefore less fossil fuels are used, less CO2 produced. We can use them for reducing pollution. So this is catalytic converters. They stop some of the nasties that are toxic to us at ground level coming out, or convert them to something that's less dangerous. They may produce us specific products, yeah, one item or another. So we've got heterogeneous catalysis, different physical states to the reactants. Okay, this happens in all of those processes. Okay, finely divided. Why would we want the catalyst to be finely divided? Because then we've got a bigger surface area. Okay, more collisions. Okay, in a support medium, maximize the surface area. So, you know, catalytic converter, the platinum and rhodium and rhenium are placed on a medium to keep them in place and stop them from being lost. Okay, we've got 3 steps. You should be able to remember that those 3 steps are, yes, that's right, adsorption, okay, reaction and desorption. Okay, and in the adsorption, something lands on the active site and forms a bond. It's going to weaken the rest of the molecule because it's forming a bond with the metal or metal oxide, which is your catalyst. Okay, and then the bond weakens, and then we have a reaction, and we've got in the right orientation, it makes it happen better. The chances of favorable collision take place are much higher. And then finally, once we've got the atoms to be rearranged in new products, the products are released. And here's a little animation which you've probably seen before last year. Okay, here is the substance coming in. Okay, it forms a bond with the catalyst or the surface of the catalyst. The other product comes in, and because the first product or first reactant is held in place, we then get a reaction happening, and we can get that the 2 new chemicals are made. Okay, right. So homogeneous catalysis is when they're in the same phase. So yeah, you usually more than one reaction step because we need to reform our catalyst. The catalyst actually takes part in the reaction but is reformed, and its oxidation state will obviously change. So here is a reaction here. Okay, and you know, why is that reaction slow? Because you've got 2 negative ions. Okay, so we could use a catalyst, which would be a positive ion. That would help things speed up a bit, and we can pop that in. It'll go faster. And here, the thiosates, well, all of the chemicals there are in aqueous format. And then if you put iron 2 plus with it, it's also in aqueous format. So they're all in the same state. Okay, so be good for you to copy down this table of the key processes, the equation and the transition or catalyst. So first one is the Haber process, which you should know, and you should know that it's that equation. It's going to be catalyst of iron, which hopefully you should remember. What does it do? It provides a solid metal place for it to for the molecules to join and react, and uses making fertilizer. Okay, the next one is the contact process. And in this process, we make sulfur trioxide. But it's what we can do that sulfur trioxide later that's good, is we can actually put it in with water and we can make acid out of it. So sulfuric acid is a good starting material. So the metal catalyst is vanadium oxide, vanadium pentoxide. It's a solid, okay, so it's heterogeneous catalysis. So all the chemicals, the sulfur dioxide and the oxygen will join to the vanadium pentoxide for a short while. They'll be held in place and hopefully molecules will crash in the right way. Okay, so we would use that for making sulfuric acid. Hydrogenation of alkenes. So this is when I'm taking my alkene and turning it into an alkane. So C2H4 plus H2 makes C2H6. Okay, nickel would be used for that, and you should have come across that in your organic reactions. So it's a heterogeneous catalysis. Okay, nickel is where are we doing this? Okay, but we're in a factory making some ethane. We've got our nickel. Okay, it's solid, and then we put our mixture through it, and that's important because the hydrogenation is what happens in food laboratories and food warehouses and food scaled up plants. They turn vegetable oil into margarine because people tend to prefer a solid fat on their toast. Okay, the final example, the final process is the decomposition of hydrogen peroxide. It breaks down into water and oxygen. A good catalyst is for manganese dioxide. Okay, but it will happen in every single cell of your body, and your body has biochemical systems that can make that work. Okay, so we've got a solid ionic compound, which is the MnO2, and the chemicals will absorb and desorb onto them. We can use to make oxygen. Okay, and that is it for 24.1D. There's some work to get on with. Hopefully you'll understand it and be able to work. And then when you come into class, you'll be able to ask questions to check your understanding. Okay, so we will finish the recording here.